In the world of physics, few things are taken for granted. Laws govern motion, forces interact, and predictions are made with a certain degree of confidence. Yet every so often a concept emerges that challenges the very foundation of our understanding. One such concept is Norton's dome, a seemingly simple construct with the potential to shatter the predictability we associate with classical mechanics. The challenge to Newtonian mechanics didn't come from a seasoned physicist or a renowned mathematician. Instead, it arose from the mind of John Norton, a philosopher of physics with a knack for exposing the subtle cracks in seemingly solid scientific foundations. In 2008, Norton published his now famous paper, introducing the world to his dome paradox. Norton, unlike many of his contemporaries, possessed a unique blend of philosophical insight and mathematical rigor. He delved into the history and philosophy of physics, immersing himself in the intricacies of relativity and quantum theory. This dual perspective allowed him to approach problems from angles often overlooked by traditional physicists, leading him to uncover the unsettling potential within Newton's laws. His dome paradox, a thought experiment of deceptively simple design, highlighted a potential flaw in our understanding of cause and effect. Norton argued that under perfectly idealized conditions, a perfectly smooth dome, a frictionless ball, spontaneous motion could occur seemingly without cause. This wasn't magic, it was a consequence of the mathematics governing the system. A mathematical loophole that challenged the deterministic nature of classical mechanics. The audacity of Norton's claim sent ripples through the scientific community. How could a concept so simple, so elegant, threaten to unravel centuries of established physics? Norton's dome isn't just a whimsical thought experiment, it's rooted in physics and mathematics. The dome's shape is defined by h equals 2/3 g times r to the power of 3/2. H is height, g is gravity, and r is radial distance. This equation reveals a hidden vulnerability in our understanding of motion. Differential equations model how systems evolve over time. They predict the future based on present conditions. But with Norton's dome, multiple solutions arise. The future isn't always predetermined. Imagine a ball at the apex of the dome. It could remain motionless or start rolling spontaneously. Mathematics allows for both, challenging our understanding of cause and effect. To ensure reliable solutions, mathematicians use the Lipschitz condition. Named after Rudolf Lipschitz, it guarantees smooth, predictable behavior. Small changes in conditions lead to small changes in outcomes. Norton's dome challenges this, failing the Lipschitz condition. This failure allows for multiple, unpredictable solutions. The dome reveals hidden complexities in mathematics and physics. The violation of the Lipschitz condition in the dome scenario opens a universe far less predictable than we believed. Determinism takes a significant hit. We're faced with a multitude of possibilities. Imagine our universe operates on probabilities. The ball on Norton's dome exists in a superposition of states. It could remain at rest or spontaneously roll. Classical mechanics doesn't crumble. Most physical systems are predictable. Planets orbit, objects fall, pendulums swing. But in scenarios like Norton's dome, determinism fades. The dome paradox reveals a stranger universe. It challenges our assumptions about cause and effect. The search for resolution is a search for reality. Newton's first law states that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by a net force. This law forms the bedrock of our understanding of motion. We see it every day, from a book at rest to a car cruising. Its beauty lies in its elegant simplicity. It predicts the behavior of objects with remarkable accuracy. For centuries, this law has explained the motion of objects. It allows us to launch rockets and understand planetary movements. Yet, Norton's dome challenges this seemingly infallible law. A ball rolling down a smooth dome without force contradicts inertia. How can an object at rest suddenly move without any force? This contradiction is due to our limited interpretation of the law. We apply the law over extended periods, observing macroscopic behavior. Norton's dome compels us to scrutinize the law on an infinitesimal scale. The crux of the problem lies in our understanding of causality, the fundamental principle that every effect must have a cause. Newton's first law, in its traditional interpretation, implicitly assumes a clear cause and effect relationship between force and motion. A force applied to an object causes it to accelerate, and in the absence of a net force, an object maintains its state of motion. However, Norton's dome challenges this seemingly inviolable connection. The ball's spontaneous motion suggests that an effect, the change in the ball's state of motion, can occur without a direct identifiable cause. This isn't to say that the ball moves randomly or without any reason. Instead, it suggests that our current understanding of cause and effect, at least within the framework of Newtonian mechanics, might be incomplete. This revelation, while unsettling, opens up a Pandora's box of intriguing questions. If an effect can occur without a direct cause, does that imply a fundamental randomness inherent in the universe? Does it suggest that our perception of cause and effect is merely an illusion, a simplification of a far more complex reality? These questions strike at the heart of scientific inquiry itself. If we cannot rely on a clear cause and effect relationship, how do we make sense of the world around us? How do we construct models and make predictions if seemingly spontaneous events can occur without warning? Section 3. The Illusion of Determinism. The dome paradox isn't just a philosophical curiosity, it has profound implications for our understanding of determinism in physics. Determinism, the idea that the future is predetermined by the present state of the universe, has been a guiding principle in science for centuries. It's the belief that if we know the initial conditions of a system with perfect accuracy, we can predict its future with absolute certainty. This principle has led to remarkable advancements in our understanding of the universe. It has allowed us to predict the motion of celestial bodies with incredible precision, understand the behavior of gases, and even model the complex interactions within atoms. Determinism has been so successful in explaining the world around us that it has become almost synonymous with scientific understanding itself. However, the dome paradox challenges this deeply ingrained notion of a clockwork universe governed by unyielding laws. If a ball can spontaneously decide to move without any external influence, it suggests that the future might not be as predetermined as we once thought. This doesn't imply that the universe is completely random or chaotic. Instead, it hints at a subtle interplay of determinism and indeterminism, a universe where the future is shaped by both predictable laws and an element of inherent uncertainty. This revelation has the potential to reshape our understanding of physics on a fundamental level. It forces us to reconsider the limits of predictability and acknowledge the possibility that even our most sophisticated models might not capture the full complexity of the universe. Section 4. A Universe of Subtleties. The dome paradox, while seemingly simple, has exposed a profound depth to the laws of physics. It compels us to acknowledge that even our most cherished scientific principles might harbor hidden complexities, waiting to be uncovered. The universe, it seems, is far more subtle than we often give it credit for. Rather than viewing this challenge as a defeat, we should embrace it as an opportunity. The dome paradox, with its unsettling implications, has the potential to push the boundaries of our understanding. It encourages us to develop new mathematical tools, explore alternative interpretations of existing theories, and consider the possibility of entirely new physics beyond our current comprehension. This isn't the first time a seemingly simple paradox has revolutionized our understanding of the universe. Consider the history of physics. Galileo's challenge to Aristotelian mechanics, Newton's unification of celestial and terrestrial motion, Einstein's radical reimagining of space and time. Each of these breakthroughs was sparked by a willingness to question established dogma, to explore the unknown, and to embrace the possibility that the universe might be far stranger and more wonderful than we ever imagined. The dome paradox, with its unsettling implications, stands as a testament to the ever-evolving nature of scientific inquiry. It reminds us that our understanding of the universe is a work in progress, a tapestry woven from both brilliant insights and the humility to acknowledge that there is always more to learn. The pursuit of a resolution to this paradox is a journey into the heart of physics, a journey that promises to reshape our understanding of the universe and our place within it. Section 1. The Great Debate. Norton's dome ignited a firestorm of debate. Was it a mathematical quirk or a fundamental flaw in our understanding of the universe? Skeptics saw it as a red herring, while others saw a crack in classical mechanics. The debate continues, revealing the complexities of our universe. The debate around Norton's dome wasn't just about mathematics or physics. It was about interpretation, the philosophical lens through which we view reality. Determinists saw it as a threat, a crack in their clockwork universe. Others saw it as a reminder of the universe's inherent uncertainty. The dome paradox became a Rorschach test, revealing physicists' deepest assumptions about reality. The dome paradox bridges classical mechanics and quantum mechanics, suggesting a porous boundary between these realms. Classical mechanics explains macroscopic predictability, while quantum mechanics governs microscopic uncertainty. Could Norton's dome reveal quantum effects at a larger scale, blending determinism and indeterminism? This question captivates physicists and philosophers, exploring connections between these branches of physics. The debate surrounding Norton's dome is far from over. It remains an open question in physics, a tantalizing puzzle that continues to challenge our understanding of the universe. However, the very act of grappling with this paradox, of questioning our assumptions and exploring new avenues of thought, is pushing the boundaries of scientific inquiry. New mathematical tools are being developed to better understand the behavior of systems that violate the Lipschitz condition, potentially shedding light on the subtle ways in which determinism might break down in specific scenarios. Experimental physicists are exploring ways to create increasingly precise physical systems, hoping to approximate the idealized conditions of Norton's dome and observe whether spontaneous motion can indeed occur in the real world. Philosophers of science are engaged in a lively debate about the nature of causality, determinism, and our ability to construct accurate models of reality. The dome paradox has sparked a renewed interest in the foundations of physics, forcing us to re-examine the assumptions that underpin our understanding of the universe. The quest to resolve Norton's dome is a testament to the enduring power of scientific curiosity. It is a journey into the unknown, driven by the desire to understand the universe and our place within it. Whether this journey ultimately leads to a definitive resolution or simply opens up new avenues of inquiry, one thing is certain. The dome paradox has forever changed the way we think about the nature of motion, causality, and the fundamental laws that govern our universe. Imagine you're a physicist, years spent dedicated to understanding the universe's intricate workings. Your world is built on laws, on predictability, on the reassuring notion that cause and effect reign supreme. Then, a thought experiment lands on your desk, threatening to unravel your understanding. This is the dilemma faced by physicists grappling with Norton's dome. It's not just a mathematical puzzle, it's a crisis of intuition, a challenge to the very core of how we perceive the physical world. Could our most cherished physical laws be inherently incomplete? Newton's first law of motion, the law of inertia, has stood as a pillar of classical mechanics for centuries. An object at rest will remain at rest, and an object in motion will continue in motion with the same velocity unless acted upon by a net force. Enter Norton's dome, a thought experiment challenging this principle. A ball spontaneously rolling down a smooth dome defies inertia, urging us to re-examine Newton's first law. The challenge is understanding its limitations and refining its interpretation. The Norton's dome paradox challenges our intuitions about motion, causality, and physical laws. Despite years of scrutiny, it remains unresolved, exposing cracks in our understanding of the universe. The dome's simplicity forces us to confront fundamental principles of physics. It compels us to question determinism, causality, and the relationship between mathematics and the physical world. The search for a resolution is a journey into the heart of our beliefs about the universe. It reminds us that science is a dynamic process of exploration and questioning. Norton's dome continues to captivate physicists, mathematicians, and philosophers. It is a testament to human curiosity and our quest to understand the universe. The most valuable lesson may be the questions it forces us to ask. In asking these questions, we push the boundaries of human knowledge. Philosophers, on the other hand, are tackling the problem from a more conceptual angle. They're questioning our basic notions of causality and determinism. Some are even suggesting that we might need to rethink what we mean by physical law altogether. But perhaps the most exciting possibility is that the dome paradox might lead us to entirely new physical theories. Some scientists speculate that it might reveal a fourth law of motion, fundamentally changing our understanding of how objects behave. Others see it as a potential bridge between classical and quantum mechanics, two areas of physics that have long seemed incompatible. Are we on the verge of a breakthrough? It's hard to say. The history of science is full of seemingly intractable problems that were suddenly solved by a flash of insight. But it's also littered with paradoxes that remained unresolved for centuries. What we can say is that the search for a resolution to Norton's dome is pushing us to the very limits of our understanding. As it stands, the problem remains open, challenging our deepest assumptions about physics. Some philosophers argue that there might not even be a single unified version of Newtonian physics that can account for all phenomena, including Norton's dome. This fragmentation of classical mechanics is a startling possibility that few would have considered before Norton's paper. So where does this leave us, and what does it mean for the future of physics? At the very least, it serves as a powerful reminder that even our most well-established theories can harbor unexpected complexities. It challenges us to question our assumptions and remain open to new ideas, no matter how counterintuitive they might seem at first. As we continue to grapple with Norton's dome, one thing is clear. The implications of this paradox extend far beyond a simple thought experiment. It's forcing us to re-evaluate our most fundamental concepts in physics, from causality and determinism to the nature of physical laws themselves. And who knows? The resolution to this paradox, when it comes, might just open up entirely new avenues of scientific inquiry, leading us to a deeper understanding of the universe we inhabit. As we reach the end of our journey through Norton's dome paradox, we're left with a profound sense of wonder and uncertainty. This seemingly simple thought experiment has shaken the very foundations of classical physics, challenging us to reconsider our most basic assumptions about causality and determinism. The dome paradox serves as a powerful reminder that even in well-established fields like Newtonian mechanics, surprises can lurk in the most unexpected places. It forces us to confront the possibility that our understanding of the physical world might be incomplete or perhaps even fundamentally flawed. As John Norton himself provocatively stated, our natural causal instinct is to seek the first instant at which the mass moves and then look for the cause of the motion at that instant. But that is not so. It is the last instant at which the mass does not move. This shift in perspective opens up a world of new questions and possibilities. As we continue to probe the foundations of physics, who knows what other mind-bending paradoxes and revelations await us? The dome phenomenon has shown us that even the most fundamental principles of science can be challenged, reminding us to always remain curious, open-minded, and ready to question our deepest assumptions about the nature of reality. In the end, the dome paradox isn't just about physics, it's about the nature of exploration itself. It reminds us that as we seek answers to the universe's most pressing questions, there will always be mysteries just beyond the horizon, waiting to expand our understanding in ways we never thought possible.